All right, let's see. A couple of notes in here. Trying to abbreviate some stuff again. We'll talk about prop load. I don't know about prop load. I'll just go with it. I'm not going to even write this down because I don't think it's worth. The faster the prop turns, the more power it absorbs or uses. That makes sense. Varies with the cube of RPM. We're not going to do that. I will just say that 80% of horsepower is used for thrust. Used for thrust, which leaves 20% for friction and slippage. All right, I bet Phil talked about this. All those 7. I don't know. Let's do this. I'll call it asymmetric loading. Asymmetric loading. All right, you guys can tell me. Phil talked about all this. P factor. What is P factor? Come on!
As soon as you say it, oh yeah.
Blade pitch at high angles of attack.
Yeah. Nick's like, why don't you tell us what you think it is, and we'll tell you if we think it's
If you're pushing this,
We'll see it. You're right.
All right, say it again, because he's right.
Difference in blade pitch during the high angles of attack.
Difference of blade pitch on high angles of attack. Well, now I'm glad I brought this in here. Right now, this is sitting level. And if we were to measure this blade angle at what station?
75%.
75%. About right in here. You see that? About yay much. If I look over here, it's about the same dang thing. Not only about, it's exactly the same. All right? But if I were to do like this, now this blade has a whole lot, doesn't it? Can you see which way it's headed off? I mean, that's, I don't know, what do you make of that? Not quite 45 degrees. Close. And this one over here is straight up and down. So, straight up and down, not taking much of a bite. Over here, it's taking a lot of bite. So, on this particular aircraft that we're flying, I know it's a wrong prop to bring in here, because it's going that way, which side is taking a bigger bite?
It's the descending side.
This side over here is taking a much bigger bite. So it's got an asymmetric load. This has got a much higher load than that side. And so which way is it going to make the airplane go?
Right.
It's going to want to go this way, shoot off that way. Of course, this is a rear, again, a pushing prop, so everything's going to be different when you think about it going forward. But, and one of the ways I remember this is in a traditional, oh, sorry, that's something else. So we have P factor. So when we take off, it wants to pull the aircraft to one side. To what? To the left, so we have to add right rudder. So, let me see. P factor, let's say the downward blade has more pitch or angle to relative wind. And pulls the airplane. Pulls the aircraft to the left. Well, since we're on this subject, what's my other problem? Gyroscopic precession. Oh, certainly Phil mentioned gyroscopic. Oh, you guys didn't have helicopter. Okay, so gyroscopic precession is a thing that Phil's going to go over in great detail on helicopters because that's where you're going to see it. But we have that problem with aircraft too, especially tail-wheeled aircraft. So gyroscopic precession is any sort of disc that is moving, be it a solid disc or a propeller. When it's moving, you think of it as a disc. And so it's spinning, and we're going to say that it's spinning this way, because that's the way it would go. So to me, that's clockwise. To you, that's counterclockwise. But anyway, it's spinning this way. And so gyroscopic precession is that in a spinning disc, wherever you put a force, that force will happen 90 degrees later. So if this were sitting here spinning, and I could somehow, without chopping my arm off, try and push right here, it's going to make it go that way down there. I didn't think I'd be talking this. I usually bring a little bicycle wheel and I could show you, but Phil will really cover it in great detail. So in a tail-wheeled aircraft, think about it, we're sitting back this way, and so the disc is kind of slanted this way, the propeller disc. Everybody see what I'm talking about? Slanted this way. Well, and it's spinning this way.
Follow.
And what's that?
Follow.
Okay, follow. Spinning this way. When I raise the tail up, it's like I pushed right here. And so if I pushed really hard on the prop right here, where's it going to show itself? It's like I pushed right here. And so if I pushed really hard on the airplane right here on this propeller, which way is the nose going to go? Boosh, off to that way. And that's what happens in a tail-wheeled aircraft when you bring the nose up. I mean, it just shoots off to the... So I remember that. I had a customer, a much older guy, and he had a good friend of his who fought RAF. I mean, his World War II. The guy was some sort of World War II fighter hero kind of guy, had all kinds of hours, and they said, "Hey, you want to fly my Piper Pacer? It's a tail-wheeled aircraft." No, absolutely. I mean, the guy's got 100,000 hours, fought in the war. They're out in Davis, and what's different between our planes and the Royal Air Force? Well, they're all tail draggers.
They turn the other way.
Engines turn the other way. So their engines are turning this way, and when the tail comes up, it's like if I push here, it's like I push, follow? Over here, which means the nose is going to go that way, so you need left rudder. And when I say rudder, you don't give it a little bit. I mean, it's a big deal. When you're getting your tail wheel checked out, you learn to dance on these rudder pedals. It's a lot.
What did he pay for that aircraft?
So, smart guy thinking, I know how to fly a tail wheel. As soon as we lift off, I'm going to be needing some left rudder. Except this is an American plane. It's already going to head off to the left. So it went off to the left, and he hit left rudder at the same time. And it went out into the field, got into some mud, and flipped over on its back. So it went over that way. So that's the way American planes are going to head. Okay. Prop clearances. This is kind of a weird subject, and prop clearances, and that you kind of have to talk about it. But things are in this weird thing. So prop clearances comes from FAR 23925. Let's try something here.
23.925.
So FAR 23.925. And
Dyson's feeder.
oops, I got an A in there. FAR. I got all kinds of numbers I didn't want in there. Let's see. Let's see if that comes up. That could be an old version right there. The thing that is exactly what I thought I was gonna find here. Here we go. This is where I normally go for my FARs. Oops, there's That's 25,925. It's not going to work. School thinks I'm looking at porn. 23. I don't think 925 exists, and that was my point. I think they pulled it. And if I had a paper copy, I would look it up. And that's why I say it's kind of a weird thing. I'm noticing things are being pulled out of Part 23. But I'm also noticing that you're still being tested on it by the FAA. So if I found a few things, and I'd have to spend some time on this, but I want to say last time I looked, it wasn't there. And so what we have is Part 23. I'll pull that back up. Let me see. Part 23, normal category airplanes, is guidance on how to build these airplanes, right? What the FAA wants you to do. And so this is where you'd find rules and laws about what we're going to be talking about is, airworthiness standards, normal category airplanes, is the distance that you have to have between the propeller and certain items. Except now I can't find it in FAR 23, except I can find it in some of the questions that you have to answer on the test. Last I looked. So it's kind of weird. But where I'm going with that is that what is interesting is that we're going into this period where they start looking more at a lot of aircraft are being designed, built, and certified to ASTM standards. American Society for Testing Materials. And so what that is, instead of the FAA coming out and saying, all right, airplanes must conform to this. You must have this exact ground clearance for props. You must have this painted that color. You must make the venting system do exactly that. They're kind of taking a step back and saying, well, ASTM has set up these standards for vehicles. You build it and tell us how it works. And so these companies are building these airplanes outside of these standards, but using ASTM and saying, okay, this works. And then the FAA shows them, yeah, it works. So you're certified. Good to go. But anyway, the propellers, according back when we had this, and the questions you still have to answer, I've seen some of them, is minimum clearances. So you can see we have a tail-wheeled aircraft up in the air, must have 9 inches here. We have to have 7 inches. I'll write this stuff down. Seaplanes have to have 18 inches. You have 1 inch between the prop and the cabin on a twin, and a ½ inch deflection here between like this tail wheel and here. So, so some of this stuff, it's like, really? That's all you're going to give us? Okay. So we do have to have some proper prop clearances. So prop clearances, let me see, tricycle gear. What is a conventional geared aircraft, by the way? Tail dragger. So conventional is the original, the OG. Tricycle gear, minimum 7 inches between tip and ground. About that much. That's not a lot. And if you keep your plane at Lodi, you're going to be fixing your prop a lot like I am.
Does that mean it's really bumpy?
A lot of little loose rocks. What's that? Are we going to that? Oh, I'll do that. Yeah. So minimum 7 inch between. So tricycle gear, minimum 7 inch between tip and ground. That is at the taxi takeoff position. So at taxi takeoff, with gear statically deflected. Statically deflected. Statically deflected simply means the amount that a spring compresses under the weight of the aircraft. So under normal compression of the struts. If you want to talk about with the strut blown or something, then it's positive clearance. So if you follow that, it's under normal maintenance with the strut inflated where it should be in normal deflation with people and weight, you need 7 inches. If you want to talk about, well, what happens if one of the struts blows out and it falls down? Well, then it's just positive clearance. Tail wheel. Nine inches.
These are manufacturer requirements.
These are FAA
The manufacturer.
for the manufacturer.
Because I could overinflate the front tires, wouldn't get a little bit additional clearance, or put larger tires on the front, get some additional clearance on a tail dragger, right?
Well, you can go more. This is just a minimum of 7.
Okay.
They don't want you to. It's no more than 7. No, it's a minimum of 7. So tail wheel, minimum of 9. Minimum of 9 inches at taxi takeoff. Now, keep in mind that at a tail-wheeled airplane, taxi, the tail is down and the prop is up pretty high. It's when you're taking off, you bring the tail up and you're riding on the mains, the prop goes low, much lower, but you need 9 inches. I want to say one of the reasons why you need more is because, and I hate this, when you're doing a wheel landing, when you're coming in, the tail wheel, you can call a 3-point where you hit the mains and the tail at the same time, which is what I prefer. If you don't, you land on the mains with the tail up, you have to push the yoke forward to keep it on the ground. That just freaks me out. Seaplane. That's 18 inches between tip and water. Because water does a lot of damage to a prop at high speed. It's spray and stuff. Structural clearances. So 1 inch radially between tip and airplane. Tip and airplane. Like from the, it's that much between the fuselage and the prop. That's like 1 inch. How about that? 0.5 inch or half an inch between longitudinally between blades or cuffs and stationary parts. Between blade and cuffs. That's like the spinner and things that go near the prop when it's moving. Cuffs. And what else? Stationary parts. And positive clearance. Between other parts. Between other parts. Such as spinner. Be an example. Cowling. Well, what are you going to do if you have a twin engine airplane and you have less than 1 inch between the tip and the airplane structure?
Put it front prop.
Shim the engine mounts.
Shim the engine mount, dent the airplane a little bit right where the prop goes through.
Yeah,
Just a
maybe.
little ball peen hammer. If you have less than 1 inch there, it's like, what happened? That's what I want to know. Probably you're right, yeah. Engine mounts sagging or something.
I'm just thinking if you ended up having soft engine mounts after some period of time.
Yeah, they get soft.
Flex over.
Yep, they absolutely do that. Oh, if what happens if you only have 1 inch and your mounts start to get soft? Oh, yeah.
Once you take a chunk out of your nose,
Yep.
change the engine mount.
Yeah, when you start losing paint next to the
I don't know if you can take them with the hose. They'd be that far forward?
what?
I would think they'd be sitting more we're directly in line with you.
Well, they're pretty far forward. That depends on the airplane. All right, let's see. Out of room. Okay. And clear.
Can you take a minute to explain positive clearance? I don't understand.
No, there's no actual dimension. You just
Yeah.
can't hit.
Okay,
Just
positive.
can't hit.
Okay,
Negative clearance is when it hits.
got it.
So yeah, 9 inches here, 7 inches there. Or if the strut were to fail or the tire deflated, positive clearance. 18 inches here, half an inch there. All right, different types of propeller configurations. I'll let you write this one down. So 10, or actually it's 9, but I skipped something. So types of prop configurations. A tractor propeller. So this is a standard tractor configuration on an airplane called an air tractor. So tractor. Props mounted up on the front with the prop pulling. It's a good old standard. There you go. We have the pusher type. What kind of airplane's that? That's the Icon A5. One of our students who's not here, he's a CFI with Icon. They make these right up here in Vacaville. Tony. So
Did
that,
we already pass this portion of the
Looks
class?
fun.
I think so, yeah. So pusher, we got the engine mounted on the rear. More susceptible to damage from rocks kicked up by the landing gear or by spray. So they're almost always, well, for a lot of reasons, mounted much higher. I suppose if you mounted this one much lower, the prop would cut this in half right there. So that's another reason why you have to mount them high, is because you have airplane parts down below. But, yeah, again, same thing. Rocks will be kicked up from here, getting the prop.
I swear, every time I look at that, all I can think of is somebody's like,
The Wiener Schnitzel.
VW butts.
Me too.
And they're stoned and decide, you know what, I'm gonna make this a plane. And I want it to land on the water.
But it's sexy. All right, so we take the Skymaster, or in this case the O2. The rear engine is a lot higher. And they probably could have made it lower since there's nothing that would have hit, but they brought it up quite a bit higher. So you got a tractor up. It's like a mullet.
Do you
This is-
need those? Just like some fly, or like it's the back engine filled?
Okay, so I've heard all kinds of stories about this plane. I don't know how many of them are true and how many were just bunk. But, you know, one of the stories is, you know, when they first built it and they took off and they flew it, they're like, okay, let's see what happens when we shut down the rear engine. And it picked up like 10 knots. I do know for a fact that there were, an AD came out because of this. The problem with this particular aircraft is, well, first of all, they wanted to make a centerline thrust. So if you have a rating, twin engine rating in this aircraft, it's inline thrust only. You're not allowed to fly a twin with engines out on the wings because you're not trained for that. So you have inline thrust. And so one of the problems with this aircraft is, the way I understand it, is it will climb with one engine out poorly at about 200 feet per minute, which is not much at all. Again, I don't know for a fact. I've never piloted one of these, but I hear its climb rate is not very good with single engine performance, especially with the rear one, or one of them not feathered. And you want to compound that with the type of landing gear that the 337s had. 336s were fixed gear. 337s. Cessna has a really weird gear. If you've never watched it retract, it's just the most bizarre thing. It starts out like this, and then it drops down, and then the wheels twist, and then it goes back up into the belly, and this really bizarre thing. Well, when the gear drops, because it's here, and then it actually drops down quite a bit first, and twists, it creates a tremendous amount of drag. So if you take off in any Cessna aircraft and you are having problems climbing, and you're like, hey, I'm going to get the gear up, the first thing you're going to do is hit that switch. They're going to come down and drag you back down. So you do not want to do that. In fact, while we're on the subject of gear, There have been many incidents of mechanics working on Cessna gear. We have to do gear swings every annual on an aircraft, so like any good mechanic, they'll get their jacks out and they'll jack it up and they'll make sure the wheels are nice and clear, and they'll hit the hydraulic pump pack. It pushes down on the aircraft, lifts the aircraft off the jacks, then moves it forward a couple 6 inches, right so that the jacks, because the jack point is the wing, the jacks go right through the wing. That's how you get the fuel out.
Rapid.
Yes. There used to be a Cessna dealership at the hangar where I worked at. And, sorry, this distracted me. It looks like this wing is a bunch shorter than that wing. So. Anyway, yeah, talking to the guys who used to work there, it's like, oh man, they busted up a lot of brand new Cessnas. So it needs, if I remember correctly, 21 inches of clearance that drops down before you can swing it back. So, so there was that problem. But anyway, back to the AD. What would happen is in a regular side-by-side twin, you bring the power on. If one engine isn't producing thrust, you're going to know it right away. If that engine's not producing thrust, you're going this way really fast. You're, whoa, something's wrong. In the Skymaster, you bring both engines up. You can see the front one. You can't really see or hear the rear one. I mean, you can see it. You can hear it if the front one's off. You go, oh, I definitely got it. But otherwise, you don't notice. You bring the power up. You can see the one up the front. Your thrust is going in line. You're going to take off, leave the runway, and go, I'm not climbing. And you look over and like the rear engine's not on. Now you got a real problem. So the airworthiness directive is, in this one, you don't grab both throttles and go up. You grab the rear engine. You bring the rear engine up. You get forward momentum thrust off the rear. When you have positive thrust, then you bring up the front one, and then you take off and go. So that was an AD and a change to the POH. But they make a unique sound. I was walking the dog today. I'm like, Skymaster. I'm like, yeah, it was. Because the way the wind goes across it. All right, so we have some people call push me, pull you, or something like that. All right.
What was the prop configuration? Push me, pull me?
Push and pull.
Push and pull.
This one's pulling, that one's pushing.
Push and pull. Thank you.
Push me, pull you, some people say. I think they're kind of cool planes. They suck to work on. That rear engine's really tightly cowled.
Those Cal Fire ones out there look like they just took the back one out.
Back engine?
The Scout ones, the Scout like that.
Oh, OV10s? Yeah, kind of.
Just like that.
All right, let's move on. So 10 types of propellers. I like this. I'll just tell you what to write now. Types of propellers. So by the way, if the question was, what are the 2 types of propeller configurations?
Tractor pusher.
There you go. Those are the 2 types. I can't think of another one. You can combine them, but... All right, types of propellers. Types. A. We've got the fixed pitch. A rigid propeller. Blades do not adjust. Unless you really, really want to and you have a hydraulic twister. You could write that if you want. The guy with the cigarette. Push on it hard enough. All right, so we got a fixed pitch. The blade does not change. Does the angle of attack change?
Yes.
Absolutely, the angle of attack changes because the angle of attack is the chord line versus the relative wind, and relative wind absolutely changes. So that would do that. All right, let me see. B, ground adjustable. Now I just feel guilty like I'm being lazy or something, so I just can't do it, so I have to do it. Can't be lazy. Types of props. A fixed pitch. What happens tomorrow? Dulce will just give me a bad time about it. Yeah, I said your name. What's that? I know. Actually, I didn't know. I just assumed. It's rigid. Rigid prop. Blades do not adjust. We have the ground adjustable. By the way, these fixed pitch props, they're getting really hard to come by. I was at an IA renewal a year ago, and they have some nice folks from Propeller Shop in the Bay Area. It'll come to me. Who's the prop shop up there? I say it starts with an H. No, not Stockton. It's that would start with an H. It'll come to me. Really nice people. They always do the IA seminar, and yeah, they said that like Alcoa, the big aluminum, some of these big aluminum manufacturers had said because of product liability, you can't use our aluminum to make those props. So metal fixed pitch props are getting kind of hard to come by. And so what we're seeing is a resurgence of composite props, which is a fancy word if you cut them open, a wood prop with fiberglass on top of it. So composite props are making a huge comeback. MT propeller, big. I mean, everybody's talking about MT props, and they're putting them on a lot of different things. Much lighter, kind of cool looking. So anyway, fixed pitch props getting hard to come by. Ground adjustable. So ground adjustable is the blade angle can be adjusted on the ground. Well, you can try it in the air. I mean, that's your call, but blade angle can be adjusted on the ground. So here's a hub right here of a ground adjustable propeller. Blades just look like the blades. And what we have are blade clamps here and here. And if you loosen up those blade clamps, then these blades can actually rotate in the hub. So using a protractor, which you guys will do, you'll set the correct blade angle and lock those back down. So we have the ground adjustable. Then we have the two position prop. So this one has how many positions? And what are those positions? I was hoping somebody, he says left and right. I was going to say up and down. We'd both be wrong. Actually, he'd be right, more righter. Allows prop to be in either a low angle or low pitch for takeoff, or climb, or high angle for cruise. So there we go. There is a two-position Hamilton Standard prop. And I know it's a Hamilton Standard because there's Hamilton Standard stickers right there. And while I'm looking at this prop and thinking about this is an interesting, by the way. Notice how highly polished that is? I think this is the only propeller, there's only one made, I think it's this one, that can legally be polished. A lot of people out there, especially with vintage aircraft, have nice polished props. The manufacturer's instructions clearly state and paint with epoxy paint or some type of paint. So the FAA is kind of going through a period of sending out violations and notifying people that you can't have polished props. But this is a two-position prop, and we'll talk about how it works, I think, next week. But either way, it's going to be either high or low angle. So if I have it in a low angle, that's going to give me what kind of RPM? Higher RPM or lower RPM? Higher RPM. So higher RPM, lower blade angle. That's kind of like what gear in a car? First gear. That somebody has a car. First gear. So that's going to be for takeoff, climb. Then we get up there, we're going to shift into a higher gear, pull it back, we're going to go to a high blade angle with a lower RPM. All right, two position. Then we have we'll call it a controllable pitch prop. this is where the pilot can control the pitch of the blades, or angle of the blades if you like, which would be more accurate. Pitch or angle of the blades. This one I'm going to show you is a Beech. Beech, B-E-E-C-H, Roby. And this one up here I showed you was the two position, was the Hamilton standard. Hamilton standard two position. This one is the Beech Roby. All right, so notice I said it's a controllable. I did not say it's a constant speed. That's still something different. This is a controllable propeller. And at first glance, it will kind of hurt your head a little bit. Let me see. Yeah, we'll get into how they work later. But I'll just tell you right now, because you kind of look at that going, hey, wait a minute, that motor can't be spinning around. That's going to be out of balance. But this had an option for the pilot. Either they had an electric switch, if you had the really fancy one, or a little crank. Kind of like, well, you guys wouldn't know, but back in the olden days, this is how we got the window to go down. So, but anyway, a little crank, and that little crank or the electric motor would turn these pinion gear against this gear right here, and this gear right here would, mind you, this is all spinning around except gears aren't. And I'll show you next week how it has a little drive mechanism inside that would kind of go forward and back, and there's pins in the hub. So as that moves forward, it would take part of the hub, and that pin would move it, and the hub would then change pitch. So it's a controllable pitched propeller. So the pilot would just say, well, I want a little more pitch. And he would just get a little more pitch, or a little less pitch, a little less pitch. So after the controllable pitch, we have a thing called an automatic pitch. This one is just bizarre. And I'm a little sore still. I had one and somebody walked away with it. So the pitch of the blades, is fully automatic.
It's installed.
Yep. Based on aerodynamic loads. Based on loads, aerodynamic loads. The one I'm going to show you is, it's the only one I'm aware of, is the aromatic propeller. Compers aromatic. How do I spell that? I think it's with a K-O-M-P-E-R-S. Compers aromatic prop. My notes just say aromatic, but I'm pretty sure it's Compers. All right. And again, we'll kind of talk about it, but it's just bizarre system of how they install the blades, and I'll show you next week. They're like offset from each other. You can even, if you look real carefully, you can kind of see how the hub is twisted, but the blades are not. And it's all part of it with counterweights on here. And so the whole thing is absolutely automatic. There's nothing you as a pilot can do to control it. And so what would happen is it would sense at a high RPM with a loading that would indicate kind of way that the air would hit. If you were in a climb, it would sense that climb and it would put it into a low pitch. And then if you were to level out in the way the aerodynamic loads would hit it, and centrifugal twisting force and aerodynamic twisting force and all these factors into play, mostly aerodynamic twisting force I think on this one, would then cause it to go into a higher pitch. And so it did all of this completely automatic.
How did that take off?
High RPM with an aerodynamic load that indicates a high angle of attack. So it would try, I think it tries to line itself up with that angle of attack air. I actually spent a lot of time writing notes exactly how it worked, and now I won't even, I'll just tell you briefly, because it's like, it takes a long time to sit there and concentrate really hard on thinking about how it works before you kind of get it. So it's not one of those things where you can just explain it and kind of go, oh yeah, I kind of see how that works, and like a pressure carb or something. That makes sense bit by bit. It's all kind of boom, and there it is. You're like, what the hell just happened? So I just tell you about it. Then there's the constant speed. Which is the, I guess, latest generation of props. So it uses a hydraulic governor to automatically control blade angle for a set RPM. You set the RPM, and the blades are going to do what they're going to do to keep that RPM. So pilot sets RPM, engine RPM, and blade angle changes to hold that RPM. Oh, here it is. A dead prop is equal to the drag of the entire aircraft. There, I wrote it somewhere. Let's see. We have some options here. We talked about options. We have the feathering constant speed. Let me see what I got for pictures. Got the aromatic. Constant speed. There we go. Constant speed prop. These are our governor options up here. It looks like these are pretty much, it's got a speed sensor on it, I think. This one's electric. Pilot. The other ones are push-pull. So we got a constant speed. We have the feathering propeller. This one's in feather right now. You can see that the blades have gone toward the relative air coming in. So it is stopped in flight. Sometimes I think some of these pictures aren't real. They're just Microsoft Flight Sim, actually. I think they are. That's crazy. All right. That's another one. Constant speed. Yeah, we have the feathering constant speed. The regular constant speed. We'll get into that. Options, feathering constant speed or non-feathering. Oh yeah, throw this in here. Reversing, or reverse pitch. We call it beta range. So you can actually get the prop to go from thrust that's going to move you forward to no thrust to backwards thrust. You can back up into your hangar. That's not what it's for, but it's for slowing down.
You can back up with it.
Huh?
You can back up with it.
You can, yeah, but it's not what it's there for. But
Hercules have those?
Yeah.
what's that?
Hercules does that.
Mhm.
Like back up.
Yeah.
Oh yeah,
Yeah,
turbo.
Hercules back up all the time.
Yeah, I was thinking of Barons
Oh.
in small aircraft. We don't back them up into the hangar, I don't think. But
You can't run engines inside the hangar. Right?
yeah,
So,
all right. So I should say, I think all turboprop aircraft have reversing, almost all have reversing feathering propellers. Even the single engines have reversing feathering propellers. Well, I'm not sure about reversing, but it's definitely an option. King Air has reversing feathering. Well, it's twin, so they reverse. And when you go into flat pitch, where there's no thrust at all, to the negative, that's called beta range. And they actually did some of this reversing props on piston engines for a while. It's a very expensive option. In my opinion, absolutely not worth the money. Props are so stupid expensive. And when you consider the reason why in a piston aircraft you would have a reversing prop is just to save wear and tear on your brakes. The cost of a prop versus a lot of brake pads, I'm going brake pads. So Yeah, props are, geez, what would a prop be for you guys? On your fixed pitch?
6,000, 7,000.
6 to 7 for a brand new one? Yeah, and for a constant speed for me, it's not a whole lot different. About 15,000 for a new one. So, a lot of money. Okay, so we got all kinds of options there. We'll talk more about that next week. 1, 2, 3, what have I got here?
So the regular is the same as the non-feathering?
A regular, yeah, regular, just non-feathering. I don't know where I'm at here. Controllable, automatic, constant speed. I guess I'd make this G then. Test clubs. I belong to a test club. I have a card in my wallet. So, test clubs, it's a type of prop. They look like that. So they are designed to absorb the whole entire thrust of the aircraft very close to the core of the engine. This is a water-cooled engine from the looks of it, but that's to blast air along the core of the engine for cooling. We use those on all air-cooled engines when we're testing them. I wish we had one here. Oh yeah, and this really cool video that we can start with tomorrow. Let's see. Have I got anything else here we got to cover? Unless you guys